All right, I'll get started. So I'm Christopher Fadeley. I'm the Chief Technology Officer at EIZO Rugged Solutions. Many of you might not be aware of us, and what we really do is we enable GPUs to the rugged embedded form factors. And so nowadays, what that means more than ever really is NVIDIA GPUs into form factors like 3U VPX and XMC. And so GPUs have come up quite a few times during various talks throughout the show so far. Really where they started though is for one reason, that was video games. And really the only reason I'm bringing this up is there's this idea that you have a CPU who couldn't keep up with a certain operation, and there was a big need and demand for video games. And so let's come up with a coprocessor that can offload the CPU. And if we're going to do this, we might as well design it for the specific operation. And the idea came along of, instead of going the count of smaller number of cores that are very powerful, make a ton of smaller cores that is a larger array. And a couple smart people over time said, okay, pixels are great. That's one use case, but what if instead of just pixels, we do literally anything? What if we just chuck any kind of data in there? There's probably a similar problem solution for other types of data on that. And next thing that happened basically is they took this to the next level with AI at the data center and scaled it and interconnect these until next thing you know, NVIDIA is $1 trillion company and there's just this giant compute platform out there for AI. And that's good, but obviously we're at embedded tech trends, and sometimes the logic that applies at the data center and exascale doesn't necessarily apply one-to-one with what works at embedded. And so when the question's proposed of why do we use GPUs for compute at embedded, you really have to start from the base level of that question. And the curveball in my presentation here is if MOSA is one of the most important trends within the embedded field, I have to ask the question, okay, well, what's MOSA trying to achieve? Do GPUs align with this? How's it all fit together? And so if you go on and look at the various MOSA goals out there, you'll get a pretty common list of things: interoperability, reuse, future-proofing, et cetera, et cetera. And I'm sure when these goals were first kind of proposed, they were highly focused for a specific use case and need. But one of my favorite quotes out there, I think it's Socrates, but people debate. But it's really the beginning of wisdom starts at the definition of terms. And what I mean by that, really, I say this all the time to my team, is if we're doing cross-function between different things, you're going to get statements that are ambiguous, and if we don't break them down, it's going to be a problem. We won't be able to talk to each other. And each of these goals shifts over time as different agendas, different perspectives, different technologies and use cases come into play. You can lose sight of the original focus, let alone there could be many uses of this. And so you take one example, I hear this one all the time with, oh, SOSA's expensive, MOSA can be expensive, but that's another, again, ambiguous term. Because we talk short-term, long-term, over the full life cycle, maybe the maintenance. You have to look at the full perspective. And if we're not agreeing on just fundamental terms to start, that's a problem. So when I look at MOSA kind of as a whole, one of the things I look at is ambiguity is okay. You're trying to catch all as much as possible of all the different use cases out there. To accomplish as much as you can with overlap. But the key really is the solutions and what we're trying to accomplish. And flexibility is going to be important to address a lot of the ambiguity and cast a net that accomplishes as much as possible. You need a flexible solution platform to be able to address this. It's difficult to do in an embedded space, especially with SWaP-C considerations. But if I take kind of a mile-high approach and just look at our typical workflows, right? We've seen them in the RF space, the video discussions throughout the various talks here. At the end of the day, what we're trying to do is there's a bunch of different waves flying out in the environment. Someone's got to capture those, sample them, deal with it, pipe it over. Maybe it's shared memory. Maybe there's a network fabric within the system. Maybe it's over an Ethernet pipe. Maybe it's PCIe. At the end of the day, somehow that data is being taken. Someone's then organizing it because it may not be in this perfectly framed data to deal with. Facilitates it, maybe another pipe, and then someone, the last part, which I feel like gets neglected often, is we have to do something cool with it at the end. What's the point of capturing all this data if we're not going to process it? What are we doing? So if I go back to the original question now, why GPUs compute at embedded? Yes, AI is cool. Yes, exascale, all these things, awesome. But the real value when you look at the different options out there from a processor standpoint, there's a bunch of different options within the embedded space. You have custom solutions, FPGAs. And for the media people out here, this is really the main slide I want to focus on, is when it comes to a GPU, they are the true software-defined compute platform. And it goes back to their origin and that idea that instead of just one type of data, what if we do everything? What if we marry the CPU with the GPU? And what if it acts as an offload engine for anything? What if we build a giant software-defined ecosystem and a software stack around it that is ever evolving, that constantly is being improved upon, more efficient, adding different domains over time? What if we have a $1 trillion company to back this up that also can flow it down to the edge in different platforms? That's the idea here. So if you invest in an idea that you have a compute engine that is flexible, that is available to you, it can be endless. Talk about scalability, talk about upgradability, different scales. It's very important. And so if you bring this idea, again, of sample organized process down to a typical hardware interconnect, MOSA, this is where a lot of the times the GPUs that we service, you will see you have waves flying around. There's some kind of aperture that's going to take in those waves. FPGA is going to have to be there to ingest, handle that data. The CPU and GPU are married. It's a requirement that they're both together. Take that data, facilitate it, process it, do something cool with it. So this is the most common ecosystem we see. And we've talked a lot about bottlenecks and efficiencies. And if you build a flexible platform and offset each of these operations, regardless if it's heterogeneous from a high level, if you keep them separated, you can scale independently. So when we talk about 64 gigasamples per second in RF domain, if we're talking about whammy and video sensors that are getting larger and larger, you have to look at the full system and make sure it's flexible at each point, because there's no need to capture a never-ending long data if you can't, or there's never a need to process and have this giant engine if you can't capture that amount of data. And on the flip side, why would I want the most effective engine, right? Or why should I capture all of this data if I can't do anything cool with it at the end? So by breaking these down into separate flexible chunks and being able to scale both short-term in a power domain as well as a roadmap long-term, GPUs fit perfect in that processing side. They scale up if you have a small system, middle-sized system, full-sized, and again, that's over time and architecture. But the key thing, again, is the software just works and scales. It's software defined at an application level, and therefore, regardless of what's happening, maybe you update the driver, you're not going to go through a full reuse cycle, FPGA development, so on. Just add a bigger engine. So I come from a software background primarily, and so these are just kind of some examples of what we did from a software angle, but you have EOIR, you're taking in video, FPGA is going to digitize that most likely. CPU facilitates it, chuck it over to the processing, and let's do some cool stuff with it. A bunch of different platforms, object detection, tracking, filtering, so on. I can encode it, I can render it, I can do a bunch of things with it. CPU and GPU stay exactly agnostic. Nothing else changes. Change that front end. Bring it to the RF side. Keep your SDR, direct RF. Bring that in. Let's get some IQ samples. Let's do something cool with that data. Demodulate, downsample, and then once I actually have that, for example, if it were audio, you could do automatic speech recognition, AI accelerator, traditional, bunch of different things. And because it's software defined, I can combine these things, I can scale them, I can do it a bunch of different ways. Maybe originally I had a smaller GPU, I want to do 2 domains at the same time, add a bigger tank in there. But now the last curveball in my presentation is because I'm a software guy, and over the years I've kind of had to learn the hardware domain and all the alphabet soup of a lot of the things here, is I believe there's a missing element that the industry really needs to address here. And I appreciate Curtis Wright's presentation where they were kind of talking about the software element of a lot of the CPUs and needing to address this using the engines that a lot of the hardware folks make. So while it's really easy for me to break down at a mile-high perspective of sample, organized, process, and a pipe in between and everything's good to go, the missing element are these additional bars I put here that make things ever more complicated, and that's the software interconnect and packetization and delivery. And when we talk interoperability, it's all great, right? Let's put just pipes between one another and we're good to go. Software side, me, ends up picking up a lot of it at the end to fix it. And yes, it's flexible, but at the end of the day, it's hard. So from my side, we're looking at Ethernet and a lot of things. This is just some of the stuff I've seen, right? So this isn't necessarily everything, but it's an example of kind of expressing why cross-domain thought needs to be incorporated within our developments and solutions, especially as we try to cross-share solutions as much as possible. So we talked about packetization at the payload. This is a traditional Ethernet frame. The top 3 things are standard across the board, but if I'm just talking about the payload underneath, the data I want to process is just in the middle there, but there's always other stuff going around it. I come from video domains, so one of the main video domains that are pushing through is SMPTE 2110. So it's an uncompressed Ethernet video over Ethernet service. So this is a Wireshark capture that's basically a packet breakdown of an ST2110 stream of uncompressed video. It's on the standard MTU, so it's below 1,500 bytes. And it's important to look at this because that stuff around that data is important. It's time-stamping data. You may have PTP packets for precision timing, actual data about what the pixels are with the video data and where we are in the frame. And then at the very bottom, you have the actual data that you want to deal with. And this isn't just one time. ST2110, for an example, does this on a per packet basis to the point where you keep scaling and scaling. Someone has to deal with this. Most typically, it's the CPU guys have to basically pick up and deal with massaging a lot of this data to reorganize it to get to my video frame so I can do something cool with it. And it scales and it scales and it scales and it gets harder and harder. Things can end up drowning and you can't keep up. That's a software side of things. I'm just looking at the payload there, and then the other part of it is how we deliver it between entities. Ethernet is built for flexibility, but with that flexibility comes difficulty. And again, a lot of times the CPUs or the NICs will have to deal with this. So we often hear the concept of Rocky V2, which is RDMA over converged Ethernet, and it's extremely important to break through that ceiling where you can drown. And that's done basically by adding an additional layer to the Ethernet fabric on top of the payload. That gives you a little bit more definition to allow you to directly write to the memory. But with that, you have a full negotiation mechanism. This requires you to know both ends of the memory stack. They have to talk to each other. You have to set up these domains so then finally everyone can go, yep, you're good to go. CPU doesn't have to go in the way. Send my data through. I'm no longer limited by 15 gigs, suddenly I can get up to 90 gigs. But it's not that easy. Because one of the reasons we went to Ethernet, and one of the reasons we keep adding interoperability layers at the software fabric, is to ensure that there can be a multicast connection system that's stateless, in which all the different processors on the other end at any time can receive the data, and they just got to be there ready to catch it as it comes in. And once you go over to the Rocky fabric with RDMA, what you're doing is you're doing a direct memory operation. And really what you're doing is bringing a PCIe kind of concept up to the higher stack, and at that point, you're basically going point to point. And so we have this hardware flexibility, but then to unlock the full potential of the pipe and not be drowning the CPU, we have to go this route, and there needs to be an understanding of this. And the only reason I'm bringing this up is I fear there's many other things that we need to be talking about. And what I think the industry really needs to do is a cross-functional approach to open systems. And we were talking about it earlier today about how it can start very large, and we narrow it in as we get different customers and use cases involved, and you start really looking at what are we trying to do, and things can shift. Imagine if we bring that scale even larger, where we start in thinking full perspective and start thinking about software with the hardware ecosystems we build earlier, as well as the end customers and what they're trying to do.